Welcome back. Today we're unpacking a simple idea with big consequences. As sun-like stars get old, they often destroy their closest planets. This isn't a doom headline. It's a pattern we can see from several angles. When we talk about aging stars destroying planets, we're mostly talking about tides and growth. As a sun-like star runs out of hydrogen, its outer layers puff up and its structure changes. Tidal forces between the star and any close-in planet start acting like brakes on the orbit. Energy from the planet's motion is dissipated in the star, and the orbit shrinks. If the planet is close enough, it either breaks apart or gets swallowed. We've actually seen versions of this story at different stages. There are hot Jupiters whose orbits are measurably decaying. WASP 12b is the textbook example. The planet is so close and the stellar tides so strong that each year its orbit gets just a bit shorter. It's a slow-motion demise we can time with transits. Then there's the dramatic case when the star finally wins. In 2023, a sun-like star flared and dusted itself after devouring a Jupiter-sized world. Follow-up with the James Webb Space Telescope suggests the planet didn't just get swept up by a ballooning red giant in a single instant. Instead, it spiraled inward over time until the final plunge. That detail matters, because it tells us tides are a key driver well before the star becomes enormous. And when stars end up as white dwarfs, the ultra-dense embers left behind, we find heavy elements in a large fraction of their atmospheres. Those metals shouldn't be there unless the star is actively accreting fresh planetary debris. It's like cosmic chalk dust on a black shirt. You can't miss it, and it doesn't stick around unless more is falling in. Put all of this together and a picture forms. Close-in planets often dawn to survive their star's old age. To move from anecdotes to rates, we look at big samples. A 2025 survey used test data to scan almost 500,000 stars that had just started to age off the main sequence. The researchers looked for short-period giant planets, the types that are easiest to detect if they are still there. Here's the key result in plain language. Close-in giants are missing around more evolved stars. The occurrence starts around a few tenths of a percent in freshly evolved stars and drops to roughly a third of that in stars that have cooled and swelled more. The simplest explanation is destruction by tidal decay and engulfment. If close-in giants were surviving in large numbers, we'd still see them. We don't. There are caveats. Transit searches are biased toward large planets on tight orbits, and some candidates still need mass confirmation to rule out tiny stars or brown dwarfs. But even after careful vetting, the trend holds. It's a population-level fingerprint of planetary loss. The white dwarf evidence backs this up from the far end of stellar life. Heavy element pollution. In a large share of white dwarfs implies that planetary debris keeps raining in long after the luminous giant phase ends. You can argue about exact percentages and sources of the debris, asteroids, dwarf planets, sometimes even fragments of larger worlds. But it is hard to escape the conclusion. Planetary systems keep getting stirred and consumed as stars age. So what actually drives a planet to its end? Start with tides. A planet raises a bulge on the star. Because of internal friction, that bulge doesn't point exactly at the planet. The misalignment saps orbital energy and angular momentum. Over thousands to millions of years, the orbit spirals inward. If the star's outer layers are expanding and its convective envelope is deepening, tidal dissipation ramps up and the spiral speeds along. Next is thermal and dynamical stress. A hot Jupiter parked close to a bright star absorbs a tremendous amount of energy. Its atmosphere puffs up and some material escapes. In extreme cases, the star can strip gas from the planet's dayside. None of this alone guarantees destruction, but it hastens the path. There's also chemical and rotational evidence on the star itself. When a star swallows a planet, it can gulp down a shot of elements like lithium that would otherwise be depleted in the stellar atmosphere, and it can spin up a bit. Those signatures fade with time, but if you catch them, they're a smoking gun for a recent meal. Finally, the late-stage cleanup. After a star becomes a white dwarf, distant planets and belts can be destabilized by gravitational interactions. Asteroids and dwarf planets get nudged onto star-grazing paths, tidally shredded into dust and accreted. That is why so many white dwarfs wear metallic fingerprints, evidence the system kept feeding the star long after it shed its outer layers. This isn't just a curiosity for faraway systems. Our sun will exhaust its core hydrogen in about 5 billion years and enter the subgiant and red giant phases. Inner worlds are in trouble in that scenario. Earth's ultimate fate is still modeled and debated, but habitability ends long before any engulfment. The broader lesson is that planetary systems evolve with their stars, and close-in orbits are a bad neighborhood when the landlord gets old. What should we watch for next? More long baseline timing of decaying orbits like WASP-12b to nail down how fast tides work in real stars. More population studies that separate stars by precise evolutionary stage to see exactly when the close-in planets disappear. And more spectroscopy of white dwarfs to read the composition of devoured debris, rocky, icy, or something in between. For observers and fans of exoplanets, this is a moment where single spectacular events and quiet demographic studies are telling the same story. Stars don't just reshape their planets in youth, they unmake some of them in old age. And the more carefully we look, the more often we find the fingerprints. Give us a like, comment. What are your opinions on this topic? And subscribe if you are interested in knowing more about the universe.